So this is something probably a lot of you are not unfamiliar with, right? A lot of people here are systems people, so nothing here is that shocking, but I think it's still probably is helpful to spell it out that I'm giving you permission to leave Big O behind in your day-to-day work. All right, so a little bit of history is always helpful. Why do we have Big O in the first place? Because, computer scientists wanted to approximate and classify algorithms, things that are fast versus things that are slow, as the requirement or the input size grows. So that's why we use Big O. But is it true? Right? I give you 3 examples and you tell me. Binary search is faster than linear search because binary search, the complexity is log n, but linear search is n. Can you think of a counterexample where binary search is actually not faster than linear search? Sure. When you have very short elements, right? Like in particular, if you have a cache line, when things fit into a cache line, then scanning a cache line, the majority of the time it will be spent on fetching the cache line from main memory to your CPU cache, and then the time you scan through that very short amount of data is negligible compared to the hundreds of cycles you need to go to main memory. Right. Versus binary, you sometimes do some random address access, which may even hurt you in special cases. Okay. Hash map insertion is faster than skip list because hash map is constant time versus skip list is log n. Well, it turns out if you have very high level of concurrency, you have a lot of threads trying to contend over a relatively condensed piece of data structure, then it's much easier to have a lockless implementation that has low contention with skip list versus hash map. And this mistake gets repeated over and over again, especially with like observability metrics and stuff. And finally, Coppersmith Winograd, which is theoretically the lowest complexity you can get to do matrix multiplication. But the constant factor in that Big O notation is so large that I have never seen this algorithm being used in the wild. It's just theoretically optimal, but nobody ever uses it. Right? In fact, all the GPU implementations are really, really dumb because what matters is you can very predictably feed data into all these engines, and that's the fastest. All right. So, we can safely say that Big O, it does not necessarily match reality. So why is that? Why is Big O so entrenched, and where did it came from? So if you go to Wikipedia, you will realize Big O notation actually predates computer science altogether, right? It came out about more than 100 years ago by a bunch of mathematicians. So whenever you have mathematicians telling us about quantity, we're in trouble because mathematicians actually do not care about numbers for the most part. So in making this notation, so they're making a fundamental assumption, which is scaling is smooth. So you can have this nice function as you go to infinity, right? The cost goes up, but that is not how things actually work, right? So where it fails to predict reality, number one is the Big O notation focuses very much on the event horizon that is infinity, and everybody here hopefully you only need to deal with finite situations. That's the hope. Well, so whatever happens when things go to a billion may not matter if your scale is 10. And the other thing is it assumes, generally speaking, because again, mathematicians cares about spherical chicken in vacuum, right? They assume uniform computational costs. A multiplication is a multiplication, and that's the only computation that matters in your algorithm. But we all know that is not true. You can have even the same, even ALU, so the thing that does multiplication can be contended if you have different operation mixed together, right? Not to mention bandwidth can be saturated, performance can be interfered if you have a noisy neighbor. All of those things means cost is varied, right? So Big O, I think, fails for these 2 reasons. But okay, so we sort of all know that, but what's the harm? What's the harm of holding on to Big O as a sort of a rule of thumb type of guidance for complexity? I think there are 2 ways where this I have seen this in practice that as being kind of harmful. One is, when you hear something as having a very low big O complexity, you sort of automatically assign sort of lower operational cost, right, or runtime cost with it. And this may very well come back to bite you, right? Because in practice, that may not be true. So you're sort of precluding some algorithms that may not look so good on the paper, but in reality actually is the optimal choice. The other reason I think this is problematic is that there is a very clean formula telling you the complexity. Even you sort of doubt maybe you say, oh, the constant might matter, right? Things like that. You may try to correct for it. But I think the single presentation really predisposes us to think there's one algorithm. If you're factoring all the constants and sort of the details about that presentation, you'll get the right answer. While in reality, again, our world is sort of disjoint, right? When you have a single node, the performance curve is completely different from when you have a cluster of individual nodes. So having this one, again, this notation itself is hiding a lot of the real world complexities, and then it sort of tricks us into thinking things in a particular way. So what should you do instead? I think sort of this is obviously a very simplified version of what reality really is, but I think one of the things to externalize, like what really matters in real world engineering, is that we're not solving a problem in abstract. We're solving a problem in a particular context. And often what matters for this audience, right, systems problems at a particular scale, the scale really matters. So if you know you're sorting 10 numbers, then the solution probably is very different from sorting a billion. Right? So sort of externalize that scale, deciding this is the scale at which I'm solving the problem, writing it down alongside the sort of the functional specification of the problem is very important. Because at that point, you can say, if I'm sorting one number, what is the leading cost? It may not be the lookup, it may not be the multiplication, it may not be the comparison. It may be something else, as loading the data into a place where your program actually can access the data. Right? So in that situation, not only will have something things will sort of start to look piecewise, right? It may be that if you need to go to disk, the leading sort of cost comes from the syscall that goes to disk. If you fetch things from memory, right, then the leading cost is not that. You're actually paying attention to the computation you're doing. So sort of the scale helps you sort of ground you about the kind of operations you need to run. And then notice that I say operations, I didn't say operation, because you may have more than one leading cost, right, cost center. So once you have all of these things down, then you can put together a formula that, is going to be a multivariable function instead of a single variable. And you know exactly on what range you need to calculate. All right. So I think that's what should happen, except that nobody's ever going to do that. So this is what I think people really should do, which is, I would just say, don't worry too much about complexity at all, because why do you care if your sorting or lookup algorithm is optimal if it is 0.5% of your runtime and you spend 50% of the runtime contending because, 5 threads are trying to access the same file or the same region that is guarded by a lock, right? This whole complexity thing only matters if compute actually is the bottleneck. So until you profile the whole program, you don't know. So forget about what I just said. I think the thing we probably should do a lot more is just start from some seemingly reasonable. Like, you can use a stupid algorithm. It doesn't matter. We have LM now. If you don't like it, in 30 seconds, you can change everything. So just have something in there, run it, observe what the behavior is, and then find out what is costing you time, and then ask yourself the question. This is an evergreen question. How slow should it be, right? Like, should it take this much time? Should it wait? Should it, do this much computation? And then from there, just top down, optimize the thing that do matter. And then you can just forget about this big old notion completely. And then just do things by data. That's all.